We are in section 4.8, which is Newton's method. Newton's method is a way of approximating solutions to f of x equals 0 using tangent lines of f. Newton's method, we're going to guess a first approximation to a solution of the equation f of x equals 0. I want you guys to realize that where y is equal to 0, this is an x-intercept. So this is going to be an x value. 2, using the first approximation to get a second, and the second to get a third, and so on, using the formula that we need to know is x sub n plus 1 is equal to x sub n minus f of x sub n over the derivative of evaluated at x sub n. Newton's method does not always work. If your first guess, if there's a horizontal tangent line, there's other things where it's along the lines of it's too far away, or if you're looking for a certain solution rather than the one that you're approximating. So if you look down below, it says x of 1 equals x naught plus f of x naught all over f prime of x naught. So there's a curve here graphed, and this can be any curve as it says up above, and I just randomly selected x naught value. Again, just kind of going through what this means. So what I would do is I'm going to take this and I'm going to go ahead and draw my tangent line to this point. And when I draw my tangent line to this point, you will notice that I have another value down here that is going to be my x-intercept. And this value I'm going to call x sub 1. And so the x-intercept, and we'll write it down, of the tangent line gets closer to the actual x-intercept. So again, I'm going to go ahead and go up to my graph, substitute that value in, use derivatives and tangent lines, find my x-intercept again, and I can keep going with this. This would be x sub 2, and we can keep repeating this process until we get super close to the actual x-intercept that we have. And this is how a lot of times they do this on calculators to actually come up with x-intercepts when you have a graphing calculator. So we're going to go ahead and write down the x-intercept of the tangent line gets closer to actual x-intercepts. And this is where f of x would equal 0. The example on page 16 says use Newton's method to approximate the solution to the following equation correct to 4 decimal places. And they give us an equation there. It says keep going until 2 successive guesses are the same 4 places after the decimal. So first of all, this one does not tell us a starting value, and we will have to figure that out on our own. We also don't have our function written in the form of f of x equals 0, so I'm going to move all my terms over to one side. So I'm going to rewrite my function as f of x is equal to, it's 2x cubed plus x squared. And then I'm going to subtract x and add 1 to the other side, so then that way my function can be written as it is equal to 0, which is what we need in order to use Newton's method. So in order to figure out where to start my first initial guess, I'm going to go ahead and say that I need to find a value using the intermediate value theorem where f of a value is less than 0 and f of another value is greater than 0. So just messing around with some numbers, I found that f of 0 equals 1 and f of negative 2 is equal to negative 9. So by the intermediate value theorem, if you don't remember what that is, we learned that earlier, look that up. There is going to be a solution in between these two values of 0 and negative 2. So solution is going to be between 0 and negative 2. Let me write that the other way, negative 2 and 0. Okay, so this is by the intermediate value theorem. So I'm going to go ahead and just let our first value, and I can pick anything that's in there. I'm going to go ahead and say, let's let x sub 0 equal -1. So if I let x sub 0 equal -1, that's my first initial guess. I need to calculate my next value, which we'll call x sub 1, which is going to be x sub 0 minus f of x sub 0 over f prime of x sub 0. And so I have my function up above, and now I need to find the derivative of my function. So luckily it's a polynomial, so we have 6x squared plus 2x minus 1, which is our derivative. And so x naught is -1 minus, if you were to substitute in -1 into your function, you're going to get 1 out. And substituting in -1 into my derivative, we get 6 minus 2 minus 1, which is 3. This works out to be -4 over 3. And since it talks about decimal places, since we need it to be correct to 4 decimal places, I'm going to go ahead and round this to -1.3. And we'll say repeating. If you want to write out 5 or so 3s, that's fine also. In order to find the next value, we'll say x sub 2. It's going to be x sub 1 minus f of x sub 1 all over f prime of x sub 1. And you can substitute in -4/3, or if you want that to write that out as a decimal, you can too. Going ahead and doing that, we have -4/3 minus, I'm going to write out this about 7 or so decimal places. The more that you have, the better your approximation is going to be. So if you substitute in -4/3 into your function, a lot of calculator pushing here, we get -0.6296, all divided by, substituting into your derivative, you get 7. When you keep working this out, we arrive at -1.24336. And so if you were to look at the one that was right above this, this is -1.333333, and it keeps going. It says correct to 4 decimal places. So if you notice, our 4 decimal places are not matching yet, so we have to keep going. So we keep going until 2 are going to have the same 4 digits after the decimal place. So we're on to x3, which is going to be x sub 2 minus f of x sub 2 over f prime of x sub 2. And again, the least amount of rounding you have, the better your approximation will be. But going ahead and doing this, I'm going to take that value there, which was -1.243. Oops. So we have -1.243386 minus, and if I were to substitute in my derivative here, or into my function, I get -0.055165, and then divided by, substituting that into my derivative, I have 5.7892805. And then working this out, say equals, and I get -1.2338855. Looking at those first 4 digits after the decimal, you'll notice that they're getting closer to one another, but they're not exactly equal. So we keep continuing on this process until they're actually the same. So we're on to x sub 4, which is going to be x sub 3 minus f of x sub 3 all over f prime of x sub 3. And again, pausing the video, trying to plug these in on your own. We get, I'm going to copy that down, -1.2338855 minus, substituting this into your function, we get -0.000584. And into our derivative, we get 5.666679, which works out to be -1.233752. And again, looking at those first 4 digits, not there, but it looks like the first 3 are there. Technically, if you were to round, it would be super close. Last digit would be a 9 on x3 and 8 on x4, so hopefully the next one gets us there. So we're going to go ahead and do this again. So we have x of 5 is equal to x of 4 minus f of x of 4 over f prime of x of 4 is equal to, I'm going to copy down x of 4 minus substituting in that value into my function and then also substituting into the derivative. So into the function I get negative 0 point, and there's 6 zeros, and then 4049. Again, rounding that, if you want to just make that be a 4 and leave off the other digits, that's totally fine. But 5.66535, and we'll go ahead and make that be, keeps repeating a couple 9s after that, so we'll just make this be a 6. When you do, and you work this out, you get negative 1.2337519. And looking at those 4 decimal places that we have here, and even if you were to go 5, even 6, you'll notice that they do match. So this is how the calculator usually will work out solutions when you're using a graphing calculator to approximate it. So the approximate solution to this is going to be x is equal to negative 1.233, and we can even go farther and say 752. And the actual answer, if you were to use a graphing calculator and get this even closer and continue on this process even longer, is equal to negative 1.233752. And again, there's more decimal places, but well done. It's a long process to do. If you end up with something on your exam, you will definitely have one that's not going to take quite so long. It's very tedious, a lot of calculations.